best practice. So it's important that you have the two softwares that we shall be practicing. So we'll be using XRD High Score as I indicated in the previous email, and I sent another one to you by email, which is mod. So it's likely most of you will not be able to download. It doesn't need installation. You just click on the app and then it will open up. So I'm not sure if you have received that one too. Gerald, have you received that? Yeah, okay, if you just want to observe, but it's likely you'll forget some of the steps later. So maybe the best is to have your laptop or computer open and then follow the steps together. So we will not be doing it so quick. Yesterday, some people had to drag us a little bit because they missed some steps. So today will be a little slow just to make sure we get it one time so that we don't have to go back and forth. Okay, so if you have your softwares installed and your and you are ready, then we can start right away. So no, I did it somewhere yesterday. It was better than this. Let me just give it a second.
Ani.
Yeah. Good.
Ani.
Yeah. So I have to also say that it got so slow at some point yesterday because of internet. So just to let you know, yeah. So we can start now. Yes. Okay. So good afternoon again, and nice to see that we are here to do this together. No, I keep falling off. Okay, so as you can see on the screen, we have a number of softwares that I was hoping we could practice so that you have the flexibility of choosing which one suits you and which one you think you can effectively use for your refinement. So we have Expert High Score, which is not free, but you can obtain that from UL. So mod, as you can see, is free. FP, which is foolproof, is also free. Jana is free. Jade and Max, you may have to buy them, or sometime when you download, they give you 60 days to use as a trial. Then they keep bothering you with emails to upgrade, and that means you have to pay for that. So I think with the free softwares you can get the same results, and so we don't need to spend money buying those ones. So let me also make it clear that you, as most of you already know who I am. I am not a crystallographer, so that means I'm just going to share with you what I know about refinement. It may not be perfect, and you have to make up for the rest in case you don't fully understand some of the terminologies or the things that are being discussed. So with the theoretical part, I'm not going to delve into any details. I just want to demonstrate how it is done with just a little background on the theory. So most of you are already familiar with XRD. So for XRD, we are looking at three key elements, and these three key elements are the ones that determine the material property. And these are the peak positions, the intensity, and the shape. So the shape will help us to determine the area. And all these three figures will help determine the properties of the material. And these properties could be the space group, the lattice parameter, density, roughness, lattice volume, etc., etc. So we'll see all of these in details. Then also we have atomic parameters, which will be determined by dictated by the position, intensity, and shape of the Rietveld. So the diffraction patterns that you obtain from the lab is, as you would know, is a function of this crystal structure or the sample, or also dependent on the instrument. So the peak position will give you information about the unit cell parameters, which is dependent on the crystal structure of your specimen. So the property of the material that will be affected by the peak position are the absorption and the porosity. So the peak position will be dependent on these factors. Then, of course, the instrument parameter. Since we are allowed to use it on our own, and the training we get on how to use it is just how to set up the computer and put your sample. So it's very likely that most of us will have troubles with one thing or the other, especially when it's coming from the instrument. So that is also an important factor that will affect the outcome of your SRD. So the peak intensity will help determine the atomic parameters. So these are two different parameters. Unit cell and atomic parameter are different things altogether, and the atomic parameters would depend on your Wyckoff properties. Now, don't worry about this. I don't even care about them. So once we know how to determine them and where to look for them in the software, that is enough. Most of these will be generated automatically, and you don't need to bother about them. So again, absorption, orientation, and porosity will also affect the peak intensity. So the same material prepared twice may give different peak intensity because of the orientation alone can I think affect that. Then the geometry and configuration, all of this is based on the instrument. So the peak shape will determine the order or disorder, the crystallinity. For example, we can tell right away from the shape of the peak, okay, this is a broad peak, therefore it's amorphous. And this is a very sharp peak, meaning it's likely a crystalline material. So based on that, we can make a pre-judgment on the kind of material to expect. So this will be affected also by the grain size and stress strain, depending on how you process your material. And the instrument also has its contribution to the kind of peak shape you have. So sometimes it may be amorphous, but okay, let me say this. Sometimes you expect to see a very high peak, but you end up getting a medium size or small size peak. So that could be from the instrument. And these are the challenges that some of us will face, especially because you are not expert in the instrument. So what is the role of Rietveld refinement? So as most of you may be aware already, this was first introduced in the 60s by the Dutch crystallographer Rietveld. So the whole concept was to use least square approach to refine the theoretical or the calculated line profile So this is just to calculate from a known crystal structure. So that means you take the peaks from the XRD data, and as I said earlier, these peaks may not be a true reflection. They may be affected by stress, strain, or from the instrument, and that may not be a true reflection. So the whole concept is to try to align the peaks to reflect the true, because we have the theoretically profile for that same material. So the river refinement will deal at least with the overlapping reflections or overlapping peaks. Now you can see the screenshot I showed here at the bottom, that a set of general guidelines for structural refinement using the river method has been formulated by the International Union of Crystallography. So this is a very, very important tool for XRD analysis, in particular if you have crystalline materials. So for those of us that are working more on carbon, maybe we don't need to be using these refinement, but you never know. Sometimes you have other materials in it, and you have to analyze those phases. So for the refinement, it is essential that you take very good diffraction pattern or results from your instrument, and the factors that you must consider is the geometry of the diffractometer. I think this is to do with the instrument. So the instrument alignment. So if you are going for XRD training, I think it's important you get the good training on how to do these things. So these things are the factors that will determine your river refinement. So as you can see in the bottom, it's important that if the relative intensities and or the two theta values, that's the D spacing, are not correct, that is based on the instrument, based on how you treat your material, if you get this wrong, no amount of time you spend on the structure refinement will yield any results. So you have so many peaks to fit. So in one go, in one cycle of refinement, some peaks may fit, others will not, and that will go on forever. So it's important that you get the right XRD data. So the components of the refinement. So when you finish with your refinement, you are expected to see a graph like shown on the screen. So this array is pointing to the bottom line, that's the difference profile. So this difference profile is coming from the difference between the calculated or the theoretically determined based on the refinement and the experimental profile. So what you did in the XRD room, the data you obtain will align, and then the difference will be shown here. So you have the break position. Now the important thing about the refinement is that it gives you an idea of the composition. So if you take raw XRD data consisting of two different phases, yeah, you may be able to determine the phases, but it will not give you the percentage or the weight fraction of these phases. But if you do the refinement with complete alignment, then you will be able to do that. However, this is not the only way to judge. Actually, is not the most reliable way to judge if your refinement is well fit. So don't worry about these equations, just one of the long stories. So the fit for the calculated pattern to the observed. So you always have calculated and observed, or theoretical and observed. Some refer to it as simulated and observed. So data, this will give a numerical term of agreement indices, R value. So note this value, we will talk about it in the practical side. RWP, that is the weighted profile R value. So some refer to the R as reduced, some say it as revealed, whatever. So it doesn't matter what it is referred to. What is important in as far as the practice part is concerned is to note RWP. So that is the value we need to minimize when we are doing the refinement. So in order to evaluate how well the peaks which contain the structure sensitive information are fitted, an RWP value with the background contribution eliminated should be calculated. So what does that mean? So what it means is that if the background is subtracted from your observed intensities in the net intensity after the background subtraction. So in some cases you may subtract the background or you may not. So if the background is refined, then the observed value you see here, that is the OBS and the Y and the calculated here, observed, calculated. If the background is refined, then this is likely to include the background contribution. So in this case, a high background will automatically yield a low RWP value. So, and that will be used to determine the goodness of your fit. But the RWP alone will not give you the whole story. So what can we do? So for example, if you have two refinement, doesn't mean, okay, I have two, should I just compare the RWP and then say this is better than that? It may be misleading actually. So this value here is expected, and this is what you have obtained after your refinement. So ideally the two should be approaching each other. In most of the time you will never get it to be equal, and it doesn't matter, and it shouldn't be equal, but it should approach. So if one is 5, the other cannot be around maybe 30 or 40. Close around maybe about half, 10, 5, 10, 10, 8 is fine to go. So what the goodness of it is determined by this equation is simply dividing the RWP with the R expected. Now how do you get these values? These are all generated automatically by the software. Almost all the software that I have used will generate these things, so it's not something you need to bother about. You just need to know where it is reported on the software and grab that. Most of the reports and in papers they report between 1 and 5, so that means around this figure it should be okay. So that is, if you divide this, your goodness of fit should be around 1 to 5. It should be fine, especially if you see the RWP approaching the R expected in a reasonable way. So you have to note, if the XRD data is over collected, that means you, instead of running over just maybe 30 minutes, you run for 2 hours. You may collect a huge amount of data points. So if that happens, it means errors are no longer dominated by the counting statistics. You have so much data, so that is likely to eliminate errors. Then the R expected will be very small. In that case, your goodness of fit will be far greater than 1. However, if you think you don't have time, so it's better not to even take the data then, because if you rush through, say okay, you don't have time, and you take the XRD within 10 minutes or 15 minutes, then the goodness of it is likely to be less than 1, and this is actually not a good result you will get in your refinement. So in any publication, the type of refinement must be clearly indexed. The index, that the RWP, must always be clearly stated. If you don't state it, and the reviewer knowing about result refinement, they will request for it. And sometimes people reject your analysis on the refinement based on that value. So there are some common problems that one need to know. So I think this is about the last slide, the common problems. I have stated them here. This talking about this may not be very useful as in the presentation. They are only meaningful when you try to do the refinement yourself. Then you see that, okay, but let me just say, this is, for example, the background is not well fitted. So here you can see everything is well fitted. We don't have anything out of line. So that means you are good to go. But if that doesn't happen, you need to do some more analysis. For example, you can try to fix some values, which, as I said, we will consider in a minute. So this is the last one. So today we will start to practice just using the data I sent you. You can use your own raw data if you have, but I send that one so that we can all be on the same page and also see that we have the same or similar results. Then you can practice on your own XRD. So so for today we will do refinement using expert high score. Then we use mod. For the full proof and journal, maybe later we can talk about that if you guys are still interested. And for these softwares, we have access to them, and mod is particularly free. So we need some items to or files to be able to do that. So first is the raw data, which I sent to you. Then we have the CIF file, that is crystallographic information file. And we also need to obtain the unit cell parameters, which I showed you, talked about in the table here. Yeah, here. So we need to obtain these values. Then the atomic parameters. So these will be generated. This unit cell and atomic parameters will be generated automatically in the software. For the raw data, you need to get that from XRD. The C file, we can obtain that from the DOC website, the crystallographic, various crystallographic website, I should say. Now, those ones have been uploaded by different people, and you can always trace the paper from which it was uploaded, so you can obtain those information. Then there's another soft site, copper tin precursor and carbon. So we want to determine the phase fraction of copper oxide and tin oxide in the material. So to do that, we need the raw data and we need the CIF file. So I'll show you briefly how to obtain that. Okay, let me share the full screen. Yeah. So you can simply open your web browser here. Internet can be slow, so you can, I sent you this link already to you. Okay, good. So here, crystallography open database. So here you can find the CIF file. You can see here for different phases. So for example, I sent you copper oxide, not this phase. It's not this phase, it's copper oxide, not copper 2. But assuming this is the phase you want, you just click on this. It will open up, then you save it like this. So you can save it and rename it. So that's how the file I sent you was obtained. But when you open, you need to search. So if you click on search, so there are different things you can put here in these boxes about the phase you want to search. So typically, sometimes you put so many information and it's telling you not found. So you just enter the name, the elements for that phase. So for example, tin oxide, you put tin here, another box, you put oxygen, then you go to send. If you click send, then it opens up. So tin oxide, I have tin oxide here. So this is tin oxide, this is the space group, cell parameters, and the cell volume. So this site gives only this. It doesn't give more than this. So to know more about this, then you just have to open, click on the number, and it will open, and you see it's the same information that is being given. You can see all of that. So if you are satisfied with this, you go ahead and download this save file. Now another site is material project. This one, this site, when you try to open, they will ask you to register. It's not the kind of registration where you put your email and they keep piling up information. No, you enter your email, they just send you the link and it opens. That is it. They don't send any further email to you. So don't be worried about putting your email to it. So here, how do you use this? So you can see the periodic table. So if I want tin oxide, now here, let me go back here just a minute. So you see, this is I only entered tin and oxygen, and I have tin oxide. So any material that has tin and oxygen is coming up. So that means if you are searching for tin oxide with a different space group, and here they have 1,000 entries, you have to scroll down to all these 1,000 entries, which is sometimes hectic, and you keep scrolling and missing the one you are searching for. So you see, this is another tin two-phase. So however, for the material project, if you enter, where is tin here, tin and oxygen, so they appear here. Then you go to search, this turning, so it's going to give you just these phases. You see, only tin oxide phases here. So only tin and oxygen phases. So you don't want any other element in the group. So it's much easier to search from here compared to this. But both, I think, will give the same information. Now let me tell you another advantage of this. So for example, the tin oxide phase that we will use here, space group is P42MNM. So if you come here, it's the same, this one. So if you click on that, it's going to open in a new page, but you still have the. So if I open here, this is the page for tin oxide. Now you see, this material project is giving you the crystal structure arrangement. This for example, if you have done DFT, you can directly export this to the software you're using and do your calculation. Now here we have the C file here. It's also here. So if you click, you can download in whatever format you want. So you can use conventional standard, and that should be enough and match with what we will get from the COD. Now this is not the only thing you get from material project. So for example, if you have a new material that is here and you don't know the properties, here you can find the, if you look at up here, the properties have been given of this material. So the electronic structure, the phonon dispersing, we have the XRD here. So I think most of these you can take a look at them later. So if I go to XRD, so it's giving me the pattern. This is the XRD pattern which you can download and compare with your material. And the interesting thing is that they always give from 0 to like they give a wide range. Usually we will limit to about 18, but they go beyond that, so it's very useful and you can get information. So for example, from this um, band structure, we can see from here there's a little gap, therefore it has a band gap, and with a band gap of 1.4 we can say it's a semiconductor, not a good conductor. So it is very useful. So we have the tin here, oxygen here, all this information we can also obtain later in the practice. So this is where you get your files for river refinement. So either from here or from here. There are so many others. I've sent you some of the links and you can obtain that. So if you have, I sent you the safe link because I don't want, maybe some of you will not have good internet to download it quickly. So I just sent it. So you need that one so that we can begin the practice. Minimize this. Okay, so we can start our high score now. So if you are not catching up, just stop me so we don't have to go back and forth, so we can just deal with it before we go. So you can just open the raw data file, which is what is the name, XRD ML file, and that will automatically upload this way. So there are some things that may be useful for the refinement, but they are not like very necessary. Whether you do it or not, they will still they will not affect, I mean, your refinement will still proceed, but sometimes they are useful, especially if you have very tiny peaks that do not match the files you are looking for. So how do you find the information of this file? I think this is the common part that most of you have been doing, and so let me just repeat. So for this, so you first need to treat this one. Now for refinement to proceed, you must ensure that you don't have negative background figures. So for example, most of us, to make this straight, we subtract the background. If you do that, it's going to pull this below 0 and you have negative values and intensity values. So with these values you will never be able to, it will not accept. So don't do that. So oftentimes you strip the K alpha 2 from your XRD. These are just to eliminate maybe the minor peaks that in your fitting will not yield any phase. So for example, if I want to find the phases here, typically based on the material I prepared, I'm expecting copper oxide and tin oxide. So but here, do we see these peaks or what? So you are not very sure of these things. Sometimes we are not sure if they are peaks or from the instrument or whatever. So what you need to do is to determine the peaks you want. So for example, you can go to search peaks. So if we search the peaks, so you see we have so many peaks here. So if you want to see properly how they are fitting, you can just zoom in this way. So here we have one peak in the XRD, but this is giving 2 here. So that means something is not right over there. So here we have 2 peaks, but it's 1, but it's finding 2 peaks. So all you need to do is to come to minimum significance, and then maybe increase the value to 2 or 3 to 2 and search again. So you see this peak has now become 1. So this should be fine. You can check the, usually this is useful if you have double peaks. So here, yeah, there seems to be some small peak here, which is okay. This one too is fine. So with this, you can, so if you zoom in and you double click, you go back to the same original shape. So this is something you can do to determine the peaks, so that you will not have too many peaks being detected that shouldn't be part of the refinement. So if you can eliminate them, it will be very useful. So I think even this peak doesn't seem to really fit well with this. Anyway, so for this demonstration, we don't want to do a perfect refinement. It's just to demonstrate. So so if you do that, maybe you can accept, and then you can proceed. So the next step you need to do is to import the SIF file, that's the CIF files I sent you. If you have it, you can go to insert here, or you just go here. Can you all see the cursor? So here you can just click insert. It will open the SIF, the folder. Sorry, you go to the folder where you stored these files. So in your case, you have only 3. You have the raw file here, the CIF file for copper oxide, and CIF file for tin oxide. So that's what you have. So first you can if you assume you have 8 faces, you can import all at the same time. But to demonstrate something, you can, let me say, you import the first one, and you can see right away here is given a number. This number is assigned by the software and is 100%. This is because you have only one face imported. Now why is it here? So to know why it is, go to refinement control on your middle panel. So if you click, you can see here this is the same number. So this is tin oxide, so we need to check that. So if you click the plus sign there, you go to atomic composition, and you can see tin and oxygen. Now you can rename this. To rename it, just click on the number, go to the left panel, you see title, you right click, you just click, and then you change the name to tin oxide. Now once you change the name, it will change here in the peak screen, the pattern screen. You see it also will change. So in case you have many faces all giving different numbers, so if you rename them, it will be easy to identify. So you can go ahead and import the second face, which is copper oxide, and it's also given a different number. You can do the same, rename it as copper 2 oxide. Now you see the percentage has changed. Tin is 45 and copper is 54.1. So but this doesn't really say this is the composition because we have not done any refinement. Now once you import the C files, you can go ahead and do the refinement. So to do that, you go to analysis, you see refinement. So you can see start refinement, don't click yet. Now if you look at this box here, it says manual. So you can do manual refinement or automatic. So I would advise usually you go for automatic first. If you go to automatic, then it will fit it according to the needs of the software, the pattern you have provided, and if there is anything you need to manipulate further, then you switch to manual. So you can do this for manual. You have four ways to do that. You can use clinker. Frankly, I'm not sure what clinker means, but it gives the refinement, or you go to default, then you can do the size strain analysis. Both of all of this will give you a little bit of increment or improvement in the refinement. So you can either click here and go on to do the refinement, or you go to analysis, refinement, start, then you click. You see the same thing is here. So instead of going through this long process, you can just set it up here. So this start refinement, that this is for simulation. So you just click this and you see it's reading. So you can see on your screen is refining, is fitting, everything is getting to fit. So first round is done, but you can see this is not really very great. You see this is not too good. Here I guess you have. Now remember in the slide we talk about RWP, R-respected, and goodness of fit. These are the three key parameters you need to look out for. So where can we find this in this panel? So you go to global variable, just click global variables. Then on the left right panel, you go to agreement indices. So under agreement indices, you can see condition number, R-respected, profile, weighted, this is the RWP, weighted profile, D statistics, weighted distance, goodness of fit. So these are the values you need to look for: R-respected, weighted, and goodness of fit. So we see here the goodness of fit is 2.8. This is not great. So so this will help with your visualization. So here you can see it's not okay. Here the goodness of fit is also not okay. So this is a confirmation that your fitness is not proper. Now you have seen that the tin has increased from 45 to 53, which is more than the copper, which was the opposite in the beginning. So this is also an indication that you are doing the fitness, but it's still not in the best. So you can go to size strain analysis, click that again, then it will refine. So depending on your computer, the number of phases, this can take a long time or very short time. So once you click that, you check the goodness of it, you see it has reduced to from 2.4 or so to 1.5, and your R-respected, which is 4.48, is almost approaching the 5.5, which is for the value. Remember this statement, this statement here. So we should approach, and this one is try to reduce it closer to 1 is better. So we can see is quite okay. So you can continue to do this and improve. Now what happens if all you have exhausted all the automatic fitting and still you are not happy with it, then you switch to manual. We have semi-automatic, but you can directly switch to manual and then you come to manipulate. This is where it may get a little cumbersome. So you can open all the faces. Imagine this is just two faces and we have many parameters here to deal with. So automatic will pick zero shift, so but you can pick for your specimen, which is your sample, and change that. So this is manual. That means you have control over all these parameters. So you can, for example, if I go to 10 oxide and pick scale factor, then here is refine. I can change these values. Now if you want to know the significance of each of these parameters, then you go to help and open the help button. You find the file there, you search their meaning and the refinement. Trust me, you will not like it. I don't like it either. It's boring to read, so usually you can make a good guess of these values, but you should know what you are doing. Now this is percentage. Usually you shouldn't be dealing with 0%. Once you enter one value, it will affect the others. So if I change few of these and then fit again, then you can always go back to global and check your agreement indices. So you can always check to make sure this. Now if you look at the image I showed here, we have the difference profile. So where is the difference profile here? So this is the fitting, so we need the pattern. So to get your difference profile, just go in there, right click and go to show graphics, and you see here difference plot. Then you click difference plot, and that will show you the difference plot here, and also give you the brag position, which you can see here, difference plot, the brag position for the two faces. Now you can see the faces by color. Here green is tin oxide, which is here, which is the same as the peaks up here, and the gray is copper oxide. Now for each of these, the good thing is that if you plot the raw XRD here, you may not see the see the here peak position, dissipation and the count, but you will not see the HKL values. So but if you move to this, you can see the face right away. You can see on that strip there, this is the 110 face, and this peak, for example, will be the 1,1-3 phase for copper oxide, and this is for tin oxide. So you can easily label all these. I don't know, for your eyesight, if this is not clear, you can always increase the size to see it, but you don't need this because you will export the raw data to plot. So how do you export these data to your, say, origin? So you can go to anchor data points and just right click and copy list. So if you do this, then you just open in origin, and that is where you can replot all these face elements you find, and in the end of it you should be getting something like this. So you have the raw, the difference, the calculated, and the brag positions. So that is how you can do refinement in high score. So that is it for high score. Is there any question? If no, then I will show the second software, which is mod. So if you have mod, just right click to open just in a minute. Yeah, it's opening. Okay, this is from yesterday. Let me delete that. So if you open mode, you will see the interface is like this, which is different from the high score. And in high score we import the file, but in mode you need to load the data file. So if you Gerard, has yours opened?
It has, yeah.
Yeah, good. So that means if you have it, then it should open by now. So this is actually very simple software for river refinement, and it also provides some other information. Okay, so but before I proceed with that, let me say something on this. I almost forgot. So here you can do the structure plot. You can do the structure plot. So for example, if you go to structure plot, you just click update. It will take some few seconds. Okay, yeah. So you can see this is the structure of tin oxide. Now it looks this way, but if you export it to Vesta, for example, you get a better view or idea of how that is. I don't know what happened to my app here. The Fourier face has kind of disappeared, so maybe you still have it on yours and you can do that. So you can see the quantification here. So if you want this on this face, you just need to click this symbol here, and it will just be here. If you don't want it, you just take it out. Yeah, so that is it. So back to mod. So mod is actually very simple. If you go to file, if you have a file that you were processing and you saved it, then you can open. Otherwise, you load data file. So if you click on that, you find, what did I say, my data file. So you just locate your data file and load it. So let me yeah. Yeah. Yes. So you can always move this. So this is the raw data file, just like in the here, the same file. So this is the file. You can again name the file. If you will just double click, it will open this. Then you put the name. So let me just say copper oxide plus tin oxide. Okay. Then the next is face. You click the face. So if I go here, you can insert the same procedure, but it's much easier. You just pick and drop on the upper panel, not here, upper panel here. Then this one will show you the number, just like in the high score. It will give you the elements, the name of his calcitride. So I didn't even know this before. I only knew this yesterday after showing it. So tin oxide is also called calcitrate. So you click and then good. Now again, if you have many faces, you can pick all of them and drop at the same time. Now you can also change this, just double click and put tin oxide. Yeah, so you can drag copper oxide and drop. Copper oxide also has this name tenorite, whatever. So you change it to copper oxide. So now you have all your faces uploaded. So you can go to analysis, you see compute spectra, or you simply click this calculator symbol here. You see it's the same, compute spectra, or you use the shortcut Control M. So I'll just click computer spectra. So you see it has generated the calculated pattern and the difference profile at the bottom here. So this software has some more interesting information. For example, this part is amorphous. We don't want to refine that because sometimes the software tries to fit every seemingly available peak, and because of that is having effect on other peaks. So you can really tell this software not to fit here, this section. So let's say from 0 to 20, we don't want to fit that. So you can go to the data set and click this I symbol here. When you click that, it will open this interface. Then you go to exclude region. If you go to exclude region from 0 to 20, you can enter that 0 to 20. You don't want to fit that. Once you enter that, then the software knows what you want. You want to fit from 20 up to 80. Now you have finished with this, then you see this light bulb here. It says open refine wizard panel, or you go to analysis and click wizard. It's the same. So for example, this is wizard, it opens this. If I close that and go to the bulb, it opens the same thing. So usually I go the shortcut. Now these are the various parameters you can click on to try to fit. So now we can just try with this backgrounds and scale parameters. You just click OK, then it's giving you the fit. Now here at the bottom we can see here RWP value. We can see the expected value here. So expected value here is 2 and this is 22. So this is really not good. And you can see again 10 is very low here, 49. If you look at here, 10 is 53. So this means the fitting is not okay. It's just an indication that it's not okay. So you can go back, just select any of these and you keep plotting. It's reading, you see the changing and it's fitting here. So we have some changes happening 2 to 5. We can look here on this one. Here we have 4 and I think 5. So this is pretty closer compared to this, and the weight fraction 53.5 for 10, and here is 55. So these different softwares will give slightly different values. What is more important is for you to cross-check these peaks to see their fitting. So it's just similar to the high score. You can easily zoom in to check. You see this seems to fit even pretty well compared to what we see in high score. Now, if I'm doing refinement, I just do the two and pick the one that will give me the best results, and it can be time consuming sometimes. So basically, this is what you can do here. Now, there are some other information you can find here. You can go to the bottom panel and also change these parameters. Again, just like in the high score, this will give you so many values you can vary to fit your refinement. So you can also see the 2D plot. If you click like this, you can see this, which you can directly copy to your analysis. And you have residual 2D plot here. So if for any reason you mess the system up, you can just click the hammer symbol here to fit everything back to order for you. And usually you can, it's like nailing it back to. Then this symbol here, plot selected data, you can use this to clearly see what you want. So here we did not want the 20 part, so you can right click, go to scale and change from 20 to 80, and you can see the if you want to raise this axis upward, you just go and increase it maybe to 300. This peak here is way too high, so you can increase this to bring it down. Then you can see like this. So you can directly copy this, or you export here. Tools, export experimental computer data. So that is what you can get from this software. And there are so many other things, but this is just the basic on how to get it. Now, if you look at high score, we can only trace the black positions based on the color here, but in mode you can see it's here, it's labeled, and you can see it like this. So this is something you can just directly copy and plot, or you export the raw file data and then replot it. That is depending on your choice. What else can you show? Yeah, so you can also change the, if you go to graphics, you can go to plot option and change the scale. So this is 2 theta. So if you want to change it to any other, you can easily do that. So here you see you have linear plot, which is given it. If you change any of these, it will give you a different plot based on the scale type you want. Now this is interface. That is what you see on the screen. You can I'm using Windows, maybe yours may be different. If you click it, it's just to change the interface. For example, if it's nighttime or you have too much light on your face, you can change that. And so you see here, waiting for computation. Sometimes it's really annoying because you wait for long. So they provided this piano where you can easily be, if you're a piano lover, maybe this is good software for you. So I think that is all that there is to know as far as the basics are concerned. So if you are doing the same thing, then you should be getting a well-fitted refinement of the file I sent to you, and that is it for the two. Is there any question? Pero, did it work for you?
I think it.
Oh, great. So this is just now depend on you which software to use. So that is just the benefit of showing 2 or 3 softwares. With the high score, if you import your C file based on this space group, you should be able to see that from the high score. So if you go to report, you can export structure, and if you do that, you should be getting something like this. So this section is the global parameters, and most refinement will use the void function, profile function. So where the 10, this is the copper oxide phase, and it's giving this, which is what we used, and this is the tin oxide phase, and it's giving this, which is what we use. Now after your refinement, these values may slightly vary from your original lattice parameters, because it has to adjust, and because we limited some peaks. Remember, we were doing the peak selection, so all of that will have an impact. So for the 2 softwares, I think that is it. So the other 2 that I think I will not show today. Let me just make. So it's this, you can see on the screen. I have match here. I have Jana and foolproof. So this is foolproof. That is it. That is all the software. All that I'm moving, you can see that is just the software. And this is also Jana. So these are all easy software depending on what you want. And sometimes if it's not fitting well, for example, you see here we have the difference profile. We have this long sharp peak and this, which are all indication of not being a good fit here and here. But if we go to here, we can see it's much better here compared to here. So depending on the material you are fitting, then you may decide the software that will give you a better looking results that you can really publish. So I think so that is it for now. If we don't have any further questions or anything to discuss, then maybe I'll come up with the date for this, and if you are still interested in them, then you can participate, or you can download it and try to learn it on your own.